This is section 9.1 of Rosen. We're talking about relations and their properties. Here are the topics covered in this section. This section is on binary relations, that is, relations between two sets. So here we have a definition. A binary relation, we'll call it R, from a set A to a set B is a subset of the Cartesian product of A and B. A and B do not need to be the same set or even have the same type of elements. Here's an example. Have a set A containing the integers 0, 1, and 2, a set B containing the letters A and B. The Cartesian product of these two sets will have 6 elements, 6 ordered pairs. And we see here a subset of that, 4 ordered pairs, which would be a relation from A to B. And besides just writing down the subset that is the relation, we can depict it graphically or using a table. On the left side, we have A, the set A represented with this column of elements on the left, and the set B's elements are on the right. And we see arrows going from the element on the left part of the ordered pair to the element on the right part of the ordered pair. We can also exhibit the relation using a table where we have A oriented vertically and B oriented horizontally. And then we have an X marking where that ordered pair, whether or not that ordered pair is in our relation. We've actually already encountered relations because a function is a type of relation. There can be relations that are not functions, but all functions are relations. Specifically, it's a relation where exactly one element of B is related to each element of A, as you'll recall from an earlier chapter. Now we have the concept of a relation from a set to itself. We say that is a relation on a set. So here's a definition. A binary relation, call it R, on a set A is a subset of the Cartesian product of A cross A, or it's a relation from A to A. Here's an example. We have the set A containing A, B, and C. The Cartesian product of A and A will have 9 elements. Here I have a relation R that has 3 elements, and you can see that its elements form a subset of A cross A. Here's another set, A, the integers 1, 2, 3, and 4. And I'm going to say that the relation is the ordered pairs AB when A divides B. Let's take a look at it. Okay, here's the elements of R. They are 1, 1 because 1 divides 1. In fact, 1 divides every integer, so 1, 1, 1, 2, 1, 3, and 1, 4 will be in R. 2 divides 2, of course, but 2 also divides 4, so those two ordered pairs are in there. 3 divides 3, and 4 divides 4. So those are the elements in our set. Note that the ordered pair 2, 3 is not in there because 2 does not divide 3. And the ordered pair 4, 1 is not in there because 4 does not divide 1. Let's take a look at an example. There's first a question. How many relations are there on a set A? Well, the relations on a set are binary. In other words, so it is equivalent to asking how many subsets are there of A cross A. And we know how many subsets there are of a set from our power set calculation. So here we're going to apply that here. If we're talking about the number of elements in A cross A, it has n squared elements when A has n elements. And the number of subsets of a set is 2 to the m, where m is the set's cardinality. So I'll just plug in the cardinality of A cross A, and where there are 2 to the cardinality of A squared subsets of A cross A, or 2 to the n squared. All right, now an example. Here we have 6 relations. The first relation is the set of ordered pairs. This is on the integers. The set of ordered pairs A, B, such that A is less than or equal to B. The second one is the set of ordered pairs A, B, such that A is strictly greater than B. The third one is the set of ordered pairs A, B, such that A is equal to B or A is equal to negative B. R4 is a set of ordered pairs such that A equals B. R5 is a set of ordered pairs is AB such that A equals B plus 1. And R6, the relation, the subset of ordered pairs AB such that A plus B is less than 3. Let's just evaluate some ordered pairs and see if they're in the set, any of these relations. Looking at the ordered pair 1, 1, is it in relation 1? Yes, because 1 is less than or equal to 1. Is it in 2? No, because 1 is not strictly greater than 1. Is it in 3? Yes, because it includes equality. 1 equals 1, and it meets the criterion. And 4 is also an equality, so 1, 1 is in 4. 1 does not equal 1 plus 1, so it's not in 5, but 1 plus 1 is less than or equal to 3, so it is in relation 6. Or how about 1, 2? 1 is less than or equal to 2, so it is included in relation 1. 1 is not greater than 2, nor is it equal to 2 or it's negative. And for R4, it's not equal, so it's not in that one. And it's not equal, 1 is not equal to 2 plus 1, so it's not in R5. But 1 plus 2 is less than or equal to 3, so it is in relation 6. How about 2, 1? 2 is not less than or equal to 1, so it's not in 1. But 2 is strictly greater than 1, so it is in 2. 2 is not equal to 1 or it's negative. And it's not equal, so it's not in 3 or 4. 2 is equal to 1 plus 1, so it is in 5. And it is also in 6 because 2 plus 1 is less than or equal to 3. All right, how about 1 and negative 1? Well, 1 is not less than or equal to negative 1, so it's not in 1, but it is in 2. 1 is greater than negative 1. And notice that it is in 3 because we have A is equal to negative B, so it's in 3. It's not in 4, it's not in 5, but it is in 6 because 1 plus negative 1 is less than or equal to 3. All right, and finally 2 and 2. 2 is less than or equal to 2, so it's in 1. 2 is not strictly greater than 2, so it's not in 2. It's in 3 because of equality. It's in 4 because of equality. It's not in 5, and it's not in 6 because 2 plus 2 is not less than or equal to 3. And I have the solutions to all of these. Hopefully we got these right. 2, 2 is in 3, 1, negative 1 is in 3 of them. 2, 1 is in 3 of them. 1, 2 is in 2 relations, and 1, 1 is in 4 of them. Okay, so we got it right.